When we're working with synthesis for aromatic compounds, a lot of times these kinds of problems come down to making sure you put the groups on in the correct order. You know, in this first question, we have two relatively simple groups to put on here. The nitro group, and we know we can put a nitro group on through direct nitration, and the carboxylic acid. And there's actually a whole bunch of ways we could make the carboxylic acid. We could make it by putting an alkyl group on and then oxidizing with permanganate. We could put a methyl ketone on with an acylation and then convert that to the acid, as well as doing things like making a Grignard and adding to carbon dioxide. The biggest key, and we'll go through one of those possible routes in this solution, the biggest key is to just make sure we do things in the correct order. And so we know that we can make carboxylic acid. We've learned a number of different ways to do that. But perhaps the easiest is to make it from a halogen, such as a bromide, where you add magnesium, followed by adding that Grignard to carbon dioxide. And upon quenching that with acid, we yield the carboxylic acid. So that's our first step. Or, when we first step retrosynthetically, if you're thinking about this in the forward direction, this would be our last step. We then need to put each of these groups on, because just note that all of these synthesis questions were starting from benzene. Now, the bromine itself, while it's a deactivating group, is an ortho-para deactivator. And the two groups that we have arranged here are arranged meta. But the nitro group is a meta director. And so if we had nitrobenzene, and did a bromination of that, then that nitro group would direct any new substituents, in this case the bromine, meta, and we get the substitution we wanted. Finally, the nitro group can be added in a single step directly to benzene, and we do that using the nitration conditions of nitric acid, sulfuric acid, and heat. All right, our second question, we've got now 3 different groups on here. And what's going to also complicate this is one of them is an alkyl group. Given that one of them is an alkyl group, we've learned that usually the easiest way to add in an alkyl group is with a Friedel-Crafts reaction, whether alkylation or acylation. Now here we want 3 consecutive carbons, so that means we're probably dealing with an acylation, because if we tried to do this with an alkylation, we'd end up with the predominance of the rearrangement and the isopropyl group. We also need to put it on first because the other 2 groups, the chlorine and the sulfur group, are both deactivating groups, and deactivating groups don't support the Friedel-Crafts reactions taking place. So if we start with our Friedel-Crafts acylation, we get our 3 carbon group on here. Now that acyl group that we've added is an electron withdrawing or a meta-directing group. So we could use this to direct any group that's going to be meta to this chain. The group that's meta is the chlorine. So we can then do chlorination, which will take place at the position meta to the carbonyl. Now, from here, there's two additional steps. One is the removal, the reduction of the carbonyl to give us the alkyl chain. The second one is the sulfonylation. And we need to figure out, does the order matter? So in other words, do we want to reduce first and then do sulfonylation? Or do we want to try and do sulfonylation and reduce after? What's going to determine which one of those paths is correct is the path that's going to give us the correct substitution. So if we try to do sulfonylation first, we have our alkyl group, which is a meta director. It's going to direct new substituents to that carbon. The chlorine, on the other hand, is an orthopara deactivator, which want to put new substituents at those positions. So we can see that's probably not going to be very helpful because we've got just too many possibilities, and the two groups are not working together to give us the substitution that's desired. So that means we probably want to try reducing first. If we reduce first, that chlorine, still an orthopara director, still directs to those three positions. But the alkyl group now, also orthopara, and will direct to the same three positions. Now we can make a case for at least some selectivity. We're probably going to see the least amount of substitution at this carbon, and the reason for that is it's between the two substituents, so probably less reactive due to sterics. But it is true that the sulfonylation will probably give us a mixture of substitution at those two carbons. In some cases with aromatic substitutions, that's the best we're going to be able to do, is to assume we're going to get a mixture, and then once the reaction's done, we'd have to try and separate it. But that will at least get us some of our starting material converted to the desired product here. All right, in part 3, we're going to try and make acetaminophen directly from benzene. And there's a couple things that should really jump out at us. One is we have an alcohol group there. And at this point, we've really only learned one primary method for making phenols. And so that means we're very, very likely to need to go through a diazonium salt. There are other ways, but at this point, we may not have gone through them yet. And if we're going to go through a diazonium salt, that means we're going to need to start with nitration. So we're just going to kind of outline our synthesis. We can come back and fill in the reagents later. We put on the nitro group. Now, nitro groups are orthopara directors, so we don't want to use this nitro group to direct our other group in. But if we reduce the nitro to an amine is an orthopara director, and so we could then use that to direct another group in. Again, as with question 2, at this point, any reaction we do is probably going to give us a mixture of isomers, and we're just going to assume that we can separate them. Now, what group do we want to put on there? So we know on one end of the molecule we needed a nitrogen because we're going to convert it to the diazonium salt and eventually to the alcohol. On the other side, though, we have the amide. So we're actually going to need another nitrogen. Again, we're probably going to get some ortho as well. We're just going to assume we get a mixture and we can separate out the isomers. From here, it's really just a matter of converting each of these nitrogens into the functional group that we need. The amine up at the top, if we add acetyl chloride to it, will form an amide. And to finish this, we need to go through the sequence of steps that's going to allow us to convert a nitro group first into an amine, then that amine gets converted first into the diazonium salt, and then finally into the alcohol. At this point, we can go back and fill in reagents. Both of our nitration steps are going to require the use of sulfuric acid, nitric acid, and heat. So that's over here as well. The reduction of the nitro to the amine can be done in a couple different ways. We'll just stick with hydrogenation. We already put in our acid chloride to form the amide. Again, we have another reduction. We'll use hydrogenation again. And finally, the Sandmeyer reaction. Using nitrous acid followed by copper oxide, copper nitrate. Our final question on this section, a little bit more complicated. We're going to be making or attempting to make ibuprofen. We can see that we've got two different carbonyl groups we're going to need to get in. So where do we want to start? Well, I look at that carboxylic acid as probably being a really good place to start. We need something that we can make into a carboxylic acid. So if I have an alcohol there, then I can use Jones reagent to oxidize that all the way up into the carboxylic acid. Now I need to make that alcohol. What method can I use for making this alcohol? Well, we know we can make alcohols from alkenes. So if I had an alkene there, I need the less substituted or the anti-Markovnikov alcohol. And so I can form that from hydroboration. But now how do I get that alkene on there? Well, I could make that alkene if I had instead a carbonyl, such as this one. And then I would just need to use acidic reaction. And finally, I could make that alkene, or that carbonyl, using a Friedel-Crafts acylation. So from here, I'm almost done. Now, again, like some of the other reactions we've talked about in this exercise, this acylation may give us mixtures of ortho and para substitution. Just something we can't really truly avoid for a reaction like this. But I've got another alkyl group to get on there. If I had a carbonyl there, I could reduce that. And finally, one last step will get us there. Ran out of room here, so you can just imagine we've got benzene, and then we would just need the appropriate acid chloride to do another Friedel-Crafts acylation.